we can now look at predicting the direction of reaction. So the reaction quotient Q is a resulting value when we substitute reactant and product initial concentrations into the equilibrium expression. So to determine in which direction a system will shift to reach equilibrium, we compare the values of Q and Kc, of Q and Kc. If Q, number one, if Q is greater than Kc, if Q is greater than Kc, the reaction will move. The reaction will move to the left. The reaction will move to the left. The reaction will move to the left. This means that the reaction will move towards equilibrium by forming more products. The reaction will move towards equilibrium by forming more reactants. Okay, then if Q is less than Kc, the reaction will move to the right. The reaction will move to the right. The reaction will move to the right. So the reaction will move towards equilibrium. Reaction will move towards equilibrium. Reaction will move toward equilibrium by forming more products. Okay, then if Q is equal to Kc, the reaction is already at equilibrium. No shift occurs. Okay, so having this, we can now determine in which direction the reaction will move to attain equilibrium by comparing the values of Q and Kc. So in this case, the value of Kc can be given. Then what we just need to do is to calculate Q, that is the reaction quotient, using the initial concentrations of reactants and the products. So let's have an example. Let's see how we can see in which direction a certain reaction may move to. Okay, so for example, for the reaction B forms 2A. For the reaction B forms 2A, Kc is equal to 2. Kc is equal to 2. Suppose 3.0 moles. suppose 3.0 moles of A and 3.0 moles and 3.0 moles of B are introduced into a 2.0 liter flask. 2.0 liter flask. Question A. In which direction will the reaction proceed to attain equilibrium? Okay. Then the other question. Will the concentration, or maybe before I go to due to the lack of space, let's first answer the first one, then we'll go to the next question. We don't have much space. Okay, so in which direction will the reaction proceed to attain equilibrium? Okay, so what we need to do here is to first calculate Q solution. Q. So in order for us to calculate Q, we need initial concentration of B and A. So we have 3 moles of A and 3 moles of B, which are in a 2 liter vessel. So we know that concentration of A is equal to the concentration of B, since they have same number of moles and in the same vessel. So number of moles, which is 3.0 moles over 2.0 liters, which is giving us 1.5 molar. Okay, so this is the initial concentration of A and B. Okay, so Q will be given as A squared, concentration of A squared, over concentration of B, So which is equal to concentration of A, which is 1.5 squared, over concentration of B, 1.5. So we can cancel that. This one goes, which is equal to 1.5. Okay, so in this case, our Q is equal to 1.5. Then now let's compare with the value for Kc. So in this case, Kc is equal to 2. So we have found that Q. So in this case, Q is less than. In this case, Q is less than Kc. So if Q is less than Kc, it means the reaction will move to the right. The reaction will move to the right, meaning more products will be formed as the system attains equilibrium. Okay, then now the second question is, will the concentration of B increase? Will the concentration of B increase or decrease, or remains the same as the system attains equilibrium? So we know that the system is moving to the right. So in this case, the concentration of B will decrease since the system moves to the right. So B, concentration of B decreases. Concentration of B in this case will decrease. Okay, so we can now look at calculating equilibrium concentrations and pressures. Calculating equilibrium concentrations. Calculating equilibrium concentrations and pressures. So we use the ICE. We can use ICE tables to calculate equilibrium or to solve equilibrium problems for KC or equilibrium amounts. Okay, so in this case, I that is initial concentration of reactants. Initial concentration of reactant usually given. Initial concentration of reactant usually given. Then products initial concentration usually assumed to be 0. So products initial concentration assumed to be 0 unless otherwise stated. Then C that is change in concentration. So we assign a variable X. We assign a variable X. So we use the stoichiometry. Of the reaction. To assign changes for all species. Then E that is equilibrium. A is equilibrium concentration. Equilibrium concentration. So E is equal to I plus C. E is equal to I plus C. Okay, so let's have an example. Let's see how we can calculate. Let's see how we can calculate equilibrium concentrations. Okay, example. So for the formation of hydrogen, fluoride, for the formation of hydrogen fluoride gas from hydrogen and fluorine, the Kc was found to be 1.15 times 10 to the power 2 at 300 degrees Celsius. Okay, 300 degrees Celsius. So this is the reaction. Hydrogen gas plus fluorine gas then forms forms hydrogen fluoride gas. So in a particular so we can say in a particular experiment, so 3.0 in a particular experiment, 3.00 moles of each component, 3.00 moles of each component, 3.00 moles of each component was added 3.00 moles of each component was added to a 1.500 liter flask. 00 liter flask. Then now calculate the equilibrium. Calculate the equilibrium concentrations. Calculate the equilibrium concentrations of all species. Okay, so now let's see how we can calculate equilibrium concentrations of these species. So we need to, first of all, we need to understand the statement here. 3.00 moles of each component was added. So we have 3.0 moles, 3 moles of hydrogen, 3 moles of fluorine, and 3 moles of hydrogen fluoride were added to a 1.0 liter flask. Okay, so now we can calculate Q to know in which direction the reaction will proceed to. Okay, so we need to know the initial concentration. So initial concentration of hydrogen is equal to initial concentration of fluorine, which is equal to initial concentration of hydrogen fluoride. Okay, so the 0 here means initial concentration. So in this case, our initial concentration will equal to 3.00 moles over 1.500 liters, which will give us 3 over 1.5, which is giving us 2 molar. Okay, so this is our initial concentration of all the species. So Q is equal to hydrogen fluoride squared over, we have hydrogen here, then times fluorine. Okay, so we substitute. So we have 2 squared over 2 over 2. So which will give us 2. Okay, so in this case our Q is equal to 2. Now we are going to our 2 so our Q, so 2 into 2, so we cancel there, so 2 into 2 is equal to 1. So Q in this case is equal to 1. Then now we compare with the Kc. Our Kc given is 1.15 times 10 to the power 2. So Q is less than Kc. Q is less than Kc. So in this case, the reaction will move to the right to attain equilibrium. Okay, so we know the direction. So now let's calculate the equilibrium concentrations. So we can write the equation: hydrogen plus fluorine, then forms hydrogen fluoride. Okay, so I, in this case, our I, so we have ICE. So I is 2.00, 2.00, 2.00. Okay, so change in this case, minus x, then here plus 2x. So equilibrium now it will be 2.00 minus x, 2.00 minus x, 2.00 plus 2x. So these are the equilibrium concentrations. Then we have the Kc. So what we need now to know, to determine, is the value for x. So we know that Kc is given, the expression for Kc. So Kc is equal to hydrogen fluoride squared, okay, then over hydrogen times fluorine which is equal to, so Kc is given, which is equal to 1.15 times 10 to the power 2. Okay, so now we substitute the concentrations here, okay, the equilibrium concentrations into the expression. So it will be 1.15 times 10 to the power 2 is equal to concentration of hydrogen fluoride, which is 2. This one here, we're using equilibrium concentration, 0.00 plus 2x squared, over concentration of hydrogen, which is 2.00 minus x, concentration of fluorine 2.00 minus x. Okay, so now this one can be simplified. 2.00 minus x, 2.00 minus x is the same as 2.00 minus x squared. Okay, so you can see that the right side of this equation, the right side of this equation is a perfect square. You can see here squared. Okay, so to solve such a equation, no need of introducing a quadratic equation, since it is a perfect square. So you simply take the square root of both sides. So if we take the square root of both sides, so it means this one will be now 1.15 times 10 to the power 2 root, then which is equal to 2.00 plus 2x over 2.00 minus x. Then now we get the square root of this number. Okay, we find the square root. Then now you cross multiply, which is very simple for you. Okay, so square root of this number you find, then you cross multiply. So you are going to find that x is equal to 1.528. Okay, so that is our x. Then we know we have now determined the value for x, which is 1.528. Then let's now calculate the equilibrium concentrations. So we now calculate the equilibrium concentrations. So for hydrogen and fluorine are equal. So concentration of hydrogen is equal to the concentration of fluorine, which is equal to 2.00 minus x, and we know the value for x, so 2.00 minus 1.528, so which is giving us 0.472 molar. Okay, then the concentration of hydrogen fluoride is equal to 2.00 plus 2x. Substitute the value of x there, multiply and do the arithmetic, so you find 5.056 molar. Okay, so that is how we can solve this equation, this problem. Okay, so we can have another example. Okay, so if it is a perfect square, you simply take the square root. You simply take the square root on both sides of the equation. It is straightforward. So let's have a different example. Okay, for the reaction, PCl5 then forms PC3 plus chlorine gas. Okay, that is phosphorus pentachloride forms phosphorus trichloride plus chlorine gas. Okay, so Kc is equal to 0.4497. Okay, that is our Kc. 1.66 moles of PCl5 is put into a 1 liter. Is put into a 1 liter flask. Is put into a 1 liter flask or container. What are the concentrations? What are the concentrations or equilibrium concentrations? What are the concentrations of PCl5, PCl3 and chlorine at equilibrium? So what are the concentrations? What are the concentrations of PCl5, PCl3 and chlorine at at equilibrium? Okay, so what we need to do first is to determine. We need first to determine the initial concentrations. Okay, so initial concentration of PCl5, is equal to, so concentration in this case, the number of moles is 1.66 moles, which is in a 1 liter container, so it means it is the same. Okay, so that is the initial concentration of PCl5. Then now what of PCl3 and chlorine? So these now be assumed to be 0. So this will be 0. Okay, 0. It's equal to 0. So now we draw the ICE table. PCl5 PCl5, then PC3C2. So ICE. So initial concentration 1.6600. Change minus X plus X plus X. Okay. 1.66 minus X, X. Okay. So now we know Kc. So Kc is equal to 0.497, which is equal to concentration of PCl3, concentration of chlorine over concentration of PCl5. So that is our Kc, which is equal to 0.497. Then now we substitute our equilibrium concentrations. So it will be 0.497 is equal to PCl3 X chlorine X over PCl5 1.66 minus X, which will now give us 0.497, which is equal to X squared over 1.66 minus X. Okay, so this is not a perfect square. We cannot get the square root of on both sides because this one is not a perfect square. Not a perfect square. So what do we do now if it's not a perfect square? Using quadratic equation. So in order for us to calculate the value for X, we need to use a quadratic equation. So you are now going to multiply. So it will be X squared. This you cross multiply. X squared is equal to 0.497x, then minus 0.825, which is equal to 0. That is now, I mean, here it has to be plus. This one, when it crosses the equal sign, it becomes plus. Okay, so you formulate a quadratic equation like that. Okay, you know quadratics, you deal with this. You know that X is negative b positive, then is square root for b squared minus 4ac over 2a. Okay, so when you solve, you are going to find X is equal to 1.19. So that is the value for X, 1.19. So now what are the equilibrium concentrations? So now we find equilibrium concentrations. What are these equilibrium concentrations? Okay, so from the table we know PCl5 is equal to 1.66 minus X. Okay, X is known, 1.66 minus 1.19, so which is giving us 0.47 molar. Okay, then for PCl3, PCl3 is equal to chlorine, which is equal to X. So for these two, the concentration is 1.19 molar. 1.19 molar. Okay, so that is how we can solve problems involving quadratic equations. Okay, so sometimes we can be given it's not always that it will be in concentration in molar. So sometimes in ICE table we can also use partial pressures. We can also use partial pressures. So the way you solve is the same, whether it's concentration of partial pressures. The calculations are similar. Okay, so now we can now look at let's look at the Gibbs free energy. Gibbs free energy. Gibbs free energy. Gibbs free energy and the equilibrium. Gibbs free energy and the equilibrium. Gibbs free energy and the equilibrium constant. So want to see how Gibbs free energy is related to K. Okay, to K or Kc, just one and the same. So the relationship between the relationship between delta G, that is Gibbs free energy, and K is as follows. Okay, the relationship between Gibbs free energy delta G naught and K is as follows. So delta G is equal to minus RT ln K. Okay, so this is the relationship. Delta G is equal to minus RT ln K, where R is equal to 8.3145 joules per Kelvin per mole. This is the value for R. Then T we know is Kelvin temperature, or temperature in Kelvin. Okay, so straight away let's look at the example. Let's see how we can calculate. Okay, example, calculate K for the reaction. For the reaction of oxygen, and nitrogen. Calculate K for the reaction of oxygen and nitrogen to give any O. At 423 K. So this is the equation. Nitrogen gas plus oxygen gas then forms nitric oxide. Okay, then delta G for this reaction is 22.7 kilojoules kilojoules per mole, kilojoules per mole, kilojoules per mole, okay, of N2. So that is the value for delta G. So now we need to calculate K. We have been given this information. So we use our equation. So solution, we are now going to use our equation for delta G and K, which is here. Okay, so we know that in this case it will be ln K. Ln K is equal to delta G over minus delta G over RT. Okay, then now we substitute. Delta G is given, which is 22. So it will be 22.7 times 10 to the power 3. It has to be in joules, okay? In joules per mole. That one, it was in kilo, so you convert it. Then over R, 8.3145 kilojoules per mole. Then times the temperature, 423K. 423K. Okay, so let's see if the units are cancelling out. So we can cancel K, the J will go, per mole. Okay, so we only have a number. Okay, so you multiply and divide, you are going to get negative 6.45. Okay, but this is ln K. So K now we know we are now going to introduce E. So K now will be E negative 6.45, which will give us 1.6 times 10 to the power negative 3. Okay, so that is the value for K. So if delta G is less than 0, then K is greater than 1. And products are favored over reactants at equilibrium. Okay, so in this case K is less than 1. Okay, then if delta G is greater than 0, then K is less than 1. Reactants are favored over products. If delta G is equal to 0, then K is equal to 1. So amount of products and the reactants is equal. Okay, is equal. It means the system is at equilibrium. Okay, then delta G less than 0 means K is greater than 1. For this situation, it means products are favored over reactants. So here products favored. Okay, then another scenario, if delta G is greater than 0, it means K is less than 1. In this case, reactants favored over products. Okay, so we can end here. Then the next topic we shall look at solubility product.